Okay. Thank you very much. Having such a teaching assistant is really a blessing. Let me emphasize again. I think taking courses in English will pay off. I would imagine if you, after graduating from this school, you probably will apply for jobs. And during the interview, you can very directly tell the interviewers that you took your courses in English, okay, to almost at least the majority of your courses in English, and probably they'll then talk to you in English, okay, and the mode will not be the same. But if they interview you in English and you can finish the interview, just like that, without any difficulty, I would say it is a big plus for interview, okay? And the reason why you can conquer such a challenge is that you have been learning in English for a long, long time. So, of course, you have some edges compared to your counterparts, okay, who took their courses in Mandarin, all right? Okay, now the second rule for sampling is that the sampling frequency, it should be determining the changing, depends on the changing speed of the signal. If the signal varies rapidly with time, I will imagine I need fast, high sampling rate, okay? On the contrary, if the signal varies very, very slowly with time, then there is probably little need for high sampling frequency, right? Okay. Now, but let us, based on these observations, derive one final rule for determining sampling frequency. Now, the first assumption we need to make is that we're assuming the highest frequency component has a frequency of omega max, okay? That is beyond omega max radio per second. This signal has no frequency components. To avoid aliasing error we just mentioned, we cannot, VDN has to be within this range. Therefore, it cannot handle frequency component at this number. So, which means N0 over 2 times omega 0 has to be larger than omega maximus. So the frequency components associated with omega maximum can be accurately, effectively dealt with, all right? Now, let me rewrite this term. This term is actually 1 over 2 N0 times omega 0. And we know that N0 is T0 divided by T, because N0 is the number of sampling points, and T0 is signal period, and T is sampling period. So by definition, N0 is T0 over T. Omega 0 remain the same, but it can be rewritten as 2 pi over T0, right? That is the definition of omega 0, which is fundamental frequency. Now, if I cancel these two 0, is that if I cancel these two 2's, then what I have is pi over T, all right? So if this has to be true, then this has to be true, all right? Now, let's assume sampling frequency is fx, whose unit is hertz, then its definition of the sampling frequency is apparently 1 over t, where t is the sampling period, all right? And then the sampling frequency, when expressed in radio per second, all right, that is omega x, then it is actually the product of 2 pi and fx. And from here, we have this result, okay? And that is 1 over omega x over 2 is actually pi t. And pi t has to be larger than omega maximum, all right? So the final result is here. This is the statement made by the very well-known sampling theorists, which tell us the sampling frequency had to be at least twice as large as the highest frequency components, the frequency of the highest frequency components of the signal which you want to process, all right? So to determine the sampling frequency, the first thing we need to know is what is the frequency associated with the highest frequency components of that signal. Now, that for audio signals, I'm sorry, what's the matter with me? For audio signals, our listening ability typically can cover the range from 20 hertz to 20,000 hertz. Okay, beyond this range, we cannot hear them, okay, unless you have a hearing capability as like a dog or a cat or a bird, okay? But for us, this is the effective hearing range for our ears. So that is the reason why when convert audio signals into digital format, we typically use compact discs to store those digital audio contents. And from here to here, it requires sampling. That is, we want to convert analog audio signal into digital audio signal. And it involves sampling. And the sampling period for CD is 441 hertz. And for PC system, the sampling frequency is usually 48,000 hertz. Why? Because it has to be at least twice as large as 20,000 hertz. Okay? So that is the reason why in converting an analog audio signal to digital format, the sampling frequency is usually this or this, because both of them are sufficiently large than twice of 20,000 hertz, all right? Okay, now let's go back to this representation, okay? Remember that I define capital omega 0 as the product of omega 0 times t. Omega 0 is the fundamental frequency of the signal. T is the sampling period. Now, remember that frequency is actually, when divided in hertz, is F, right? Okay, so omega 0 is actually 2 pi f0, and its unit is actually radian per second. So if you think of one period as, let's say, a pointer rotate this clock one cycle. One cycle of rotation is equal to one period. Then the sampling frequency is actually omega zeros. All right? And you can imagine it as the angular velocity of this pointer. All right? Now, when it comes to the conventional mechanical watch, we actually have two kinds of pointer. But for the old-fashioned analog watch, we have a sweeping hand, which is moving steadily, continuously, with a fixed radial angular velocity, right? It just rotates smoothly, continuously, time and time again. That's what we call a sweeping hand. But there is another kind of mechanical watch, which is causal watch. It has a ticking hands. It does not sweep. It doesn't function like a sweeping hand, which moves smoothly with time. The ticking hand actually jump from 1 second to the other second, to the other second, to the other second. So the unit is radial per second. So for a conventional quasar watch, this speed is actually 2 pi over 60 per second. So because every ticking, we have one ticking per second, okay? So omega zero is correspond to angular velocity. Capital omega zero somehow is somehow also similar to angular velocity, but since it operates like the digital system, so it actually its unit is per sample. How many radio per sample? Okay, so if this is what we call analog frequency, then we can call capital omega zero digital frequency. Same concept, different perspective. This has everything to do with analog systems, and this has everything to do with digital systems, because we see omega zero after sampling operation. And with sampling operations, we can actually convert the CT system into a digital or discretized system. That is the reason why after sampling operations, it make more sense to use capital omega zero than using omega zero, right? Okay, now let's go to another topic and about another very important mathematical tool, which is Fourier transforms. In the beginning, of course, we will look into its definition and some related fundamental concepts. But Fourier transform is really the next step for Fourier series. Now, what do we need Fourier series? Essentially, Fourier series is important for us because by using Fourier series, we can determine the frequency spectrum of a signal. But there is one catch. There is one limitations. Essentially, Fourier series in its basic form only deal with periodical function. Because if you look at its components, it's sine and cosine, which are all periodical functions. No matter how you linearly combine those sinusoid periodical functions, their linear combinations will always be a periodical function. All right. So Fourier transform represent the next step. That is, we can break away from that limitation. By using Fourier transform, we can actually determine the frequency spectrum for non-periodical signals. All right. Now, before introducing Fourier transform, let's review the definition of Laplace transform. This is ft a signal of interest. If I take Laplace transform of that signal, what I am doing is I times this signal with e to minus t, and then I perform integration from t0 minus to t infinity. Okay, and this is the definition of invariant Fourier transform. We also saw these two equalities before. All right. Now, I'm sorry, let me erase them. This is the definition of Fourier transform. Okay. After taking the Fourier transform, okay, after taking the Laplace transform, the signal becomes f of x instead of ft. This is the representation of the signal in the t domain. This is its representation in the x domain. After taking Fourier transform, ft transform to capital F omega. What is omega? Omega is frequency. All right. This is the definition of Fourier transform. Okay. You have a signal. If you want to know its Fourier transform, the first thing you do, you times it with e to minus j omega t, and you integrate it from t equal to infinity all the way up to t, all the way up to t from minus infinity all the way up to t equal to positive infinity. Now, if you look at and compare these two representations, they are not identical, but they do look very, very similar. Okay, there are only two minor differences. The first difference is that here I have minus s. Okay, and for Fourier transform, instead of minus s, I should just take s. I have s for Fourier transform, and for Laplace transform, and for Fourier transform, I have j omega. All right, that's the first minor difference. The second minor difference is that for Laplace transform, the lower bound of the integral is 0 minus, and for the Fourier transform, the lower bound of the integral is minus infinity. But this second minor difference really doesn't matter, provided that ft equal to 0 when t is smaller than 0. Okay, if ft is 0 everywhere when t is smaller than 0, then there is really no need to integrate to perform any integration for the portion of the t value which is negative. All right. So in this case, I can simply replace this term by 0, and it won't make any difference, provided that this is true. That is, ft is a causal signal. Now, for real control applications, this is often true because we define t as the time of the initialization of the control process, the starting point of the control process. Before control process starts its operation, everything's 0. Okay, you don't have to account for anything because it's just the store is just not open yet. Okay, now operation has not started yet. Okay, So everything can be assumed to be 0, okay? So with those two minor differences, actually Fourier transform look very, very similar to Laplace transform. So in a way, all you need to do is, for control applications, replace x by j omega. Then every result in the Laplace transform can be converted, can be translated into Fourier transform. Okay? Now, what S is in the Laplace transform? S, as we mentioned before, is complex frequency, which has a real part, sigma, and an imaginary part, omega. All right? For Fourier transform, we simply drop the real part. We don't look at them. Okay? So we only pay our attention to the imaginary part. Okay? And omega is frequency. Omega is frequency. Okay? One of the fundamental problems of Laplace transform is that what is the physical meaning of the Laplace transform of a signal, such as the Laplace transform of an audio signal, the Laplace transform of a displacement signal. There is no physical meaning. We don't know how to interpret it. But what is the physical meaning of Fourier transforms? The answer is actually very straightforward. It is the spectrum, okay, of the signal. All right? Okay, this is a graph. It illustrates the relationship between Fourier transform and inverse Fourier transform. All right? Now, let's now come up with an algorithm to help us determine Fourier transforms. The good thing about discrete time Fourier transform is it helps us to determine Dn, which represent the frequency spectrum of a periodical signals. And by using DFT, that is by using discrete Fourier transforms, we can use computer to help us determine the frequency compositions of any signals. All right? We want to do the same thing for non-periodical signals. Therefore, we want to come out with an algorithm that can help us determine the result of the Fourier transform numerically, okay, by using computer algorithm, by using digital hardware. All right? Now, how do we do that? Now, the Fourier transform, let's first look at the heading of this slide. The purpose is to find the spectrum of non-periodic signals. Okay. Now, one way to look at this periodic signal is that let's first assume my periodic signal looks something like this. Okay. So the next thing I do is I choose a signal period so that my signal will repeat itself every t0 seconds, and it go forward as well. This repetitions goes in the positive directions as well as negative directions. So essentially what we have here is a periodical signal, all right? And that periodic signal is denoted by f set squared t0 of t, where t0 apparently is a period of this periodical signal. This equality is important. It tells us that if this is the case, I can go from here to here. I can also go back from here to here, as long as t0 is infinitely large. That is, the next period will appear in the infinitely long future. That means the next period will never appear. All right, it will never appear because for it to appear, I have to wait for eternity. If it will, it will not come. Okay, nobody can wait for eternity. Okay, so that's the basic idea. All right, now let's look at this slide. Now the purpose here is to help you use discrete Fourier transforms to find the numerical values for Fourier transform. Okay, now this is the periodical signal we just talked about. Okay, let's assume its Fourier series looks something like this. This is just a standard representation of the exponential Fourier series for this function, for this signal. If this is the case, then by definition, we know dn, which is the frequency spectrum of this, is this. Okay, there is nothing fancy here. These are all previous result. All right. Now let me write out for the definition of Fourier transform here as equation 4. Okay, this is simply the definition of the Fourier transform of the signal f of t. Nothing fancy. All right. The next thing I want to do is I want to relate them. Okay, so that the DFT algorithm that can help us to determine dn can be used to help me to determine f omega. All right. Now here, I can assume, let me assume f of t is f equal to this periodical signal for this period, just like this. All right. This signal is not the same as this, but they are identical if I restrict myself at this particular range. All right. So this is true. And let's assume f of t is 0 otherwise. Okay. Otherwise, in every other place. But if t0 goes to infinity, then this periodical function becomes a non-periodical function. Okay. And then these two become the same. Therefore, if these two things, if this happens, then these two equalities actually represent the same thing because these two are the same. All right. Now, so if this is the case, then dn is actually f omega over 1 t0. If that is, you look at this part, it's actually identical with this. Okay, at least they look very, very, very similar. Now, if I have this, then these two terms are the same. The only difference now, the next difference is this. Okay, so, and the next difference is, let me point out the difference one by one. This one, that's the first difference. And then this one and this one. The final difference, 1 over t0, 1. Okay, now I know that these two things, I'm sorry. Shit. I know that these two things are the same, provided that t0 goes to infinity. So they are the same. All right. Now I know that there is a difference. dn is equal to 1 over t0 times an integral. But here, We don't have 1 over t zero. It doesn't matter. I just put it here, all right? And the final difference is that here, n omega 0 is related to omega, okay? So what I can do is I set the omega to n omega 0. And I have this result, okay? Which means if I can compute dn, then I can compute Fourier transform, all right, by using this equality, okay? Remember, this was designed to find the frequency spectrum of a periodical signal. But throughout this simple process, we have illustrated that this is true. So we can use discrete Fourier transforms, which was designed to find the spectrum of periodical signals to determine the numerical values of Fourier transform, which represent the spectrum of non-periodical signals, okay? So in the futures, the algorithm, there is only one algorithm for determining the frequency spectrum of any signal. It doesn't matter if it's periodic, non-periodic, discrete, or continuous. The only algorithm we need to use is DFT, all right? Which is what? Which is essentially this, all right? Okay. Now, the next things we want to do is after understanding, okay, I'm sorry. This page summarizes our results, okay? This is a periodical signal. This is its exponential Fourier series representations, and dn, the Fourier coefficients, can be represented by these equations, okay? If I define the Fourier transform by using this equation, then what I have done is I have shown that dn is actually 1 over t0 times f n omega 0, all right? So if the sampling and if the omega 0 is small enough, I can actually find many sampling points of the Fourier transform, many sampling points of the spectrum. We will talk about that later, all right? Now, before talking about more about how to effectively determine the spectrum of non-periodical signals, let's go back to the fundamental issue of the properties of Fourier transform, okay? Now, the first thing we do is we want to study the Fourier transforms of some useful functions. When I say useful functions, I mean these functions are typically has very importance for signal processing as well as control applications. Now, the first function we see here is impulse function. Now, if you take the Fourier transform of the impulse function, this is what you will get. No surprise, because if you take Laplace transform of if you take Laplace transform of impulse function, this is what you will get, all right? But here, it makes a lot of sense because, as I told you, Fourier transform represent the spectrum of the signal, okay? Fourier transform is a mathematical operation, okay? But the result of the Fourier transform of a signal, that is, if you Fourier transform a signal, what you will get from the Fourier transform is the frequency spectrum of that signal, period. Okay, of course, it can be divided into two parts. If you look at its amplitude, then what you will get is the amplitude spectrum. If you look at its phase, its angle, then what you will have is phase spectrum. Now here, f omega is always a real number, okay? So the phase is always 0. And this is its frequency compositions, which, what does it tell us? It tells us delta function is a very special function because when we look into its frequency components, it actually has everything. It has every possible frequency components, ranging from omega 0 all the way up to omega infinity. Not only that, all those frequency components have the same amount of contributions in shaping the impulse function. All right? The magnitude are all the same. So this is actually a very meaningful, very useful signal because it pretty much covers the entire frequency domain with equal weightings. Imagine if you excite the system with such a signals, what will happen is you make the system to face all kinds of different frequency components, fast, slow, fast changing, rapidly changing, all kinds of signals. It faces all the challenges at the same time, okay? That is the reason why delta function is an ideal testing input for systems. That is the reason why people actually make impulse hammers and use that to excite the system and see what happens. Because impulse function is a very ideal testing signals because it covers all frequency components, and every frequency components have equal weightings in synthesizing delta t. All right, the second signal is constant 1. All right, if I take a Laplace, if I take a Fourier transform of constant 1, this is what I will get. No surprise, because again, Fourier transform represent frequency spectrum, and which represents the frequency contents of a signal. What content does it have? When it comes to frequency component, the only content it has is the frequency component located at omega equal to 0, because ft simply does not vary with time. It is a constant. Therefore, in synthesizing this signal, you don't use any sinusoidal signals. All right? Let's take a 10 minutes break and come back. 有没有人承认是代签的？有吗？名字划掉了吗？